variables, but we can add new variables, new features to the machine learning algorithm and let it decide if which ones would be useful, and that may include newly discovered biomarkers. And so we feel like there's a possibility that as we introduce a machine learning risk calculator to more data, that the same overall technique, if given data that from patients that did have like short-term events, then the short-term risk prediction may become possible. So the last thing I want to mention is that if any of these directions are of interest to you, then we are looking to we welcome your interest and in terms of collaboration. So on behalf of the other co-investigators, I thank you for your attention.
Open it up for questions or comments.
As was mentioned before, you are fitting a model and testing it within the MESA population, correct?
Yes.
Well, if there are unique characteristics to MESA, it's been your model will be better because the other one is fit in different data. Another alternative you could do is take the pooled risk equation and refit it using the same variables, using the logistic model. At least you would fit the coefficients to the MESA data, and it would be a fairer comparison of the type of model that you built.
I'll say that's an interesting thing. That's true. That is something we do.
I was wondering, since your population is ethnically and racially diverse in comparison to many others, whether that has any impact on the model itself, or whether that is not a factor in the risk calculation.
Well, people were helping since there was a lot of geographic diversity in the MESA studies. We're hoping that increases the robustness of our model and its ability to generalize to other areas and include, and then, as you mentioned, the multi-ethnicity of the cohort is another thing that makes us hope that our model will be able to generalize well to the other areas.
So I have a question. So very impressive results. When you look at this different group, so one thing I just want to comment is that when you have this study where there's 300,000 cases, and your study was 5,000 cases, it is hard to overfit when you have 300,000 cases. Pretty much impossible. When you have 5,000, you have to be very careful. So of course you use tenfold validation. That's fine. But like we work with SVM quite a lot, and there's very many technical details with it. So for example, like when you do this, like how do you find the parameters for SVM? Because SVM is not like a package that you just run it. You have to tune the parameters. So the important thing when you tune these parameters, the tuning of this called grid searching and all those things, they have to be done within this tenfold validation. So sometimes people just by mistake, there's complicated stuff. When you do tenfold validation, you have to make sure truly there's nothing polluting this data, this 90% versus this 10%. And that includes the parameter search, that includes feature selection, all those things. Because it is easy to misstep and do this kind of thing. So,
but we didn't do feature selection because we only used the same feature that the ACC guidelines.
So
but you're right, when you do feature selection, then basically open a whole can.
Or like this grid search, like of the search of the parameters, because there's like this, the SVM has these parameters you have to set. So the question is how you set those parameters, and so that has to be done within this tenfold loop. So anyway.
Yes, you're right. You bring up a good point. I think one of the things that our colleagues at University of Houston, while we were doing the study, that they were very careful to wipe the slate clean between everything. It's like so that there would be no memory between any of the repeated iterations, that nothing was carried over from the previous model.
Question.
So if you have a relatively small data set, let's say Mesa 5,000, does that help you if you have, say, 100 variables, which you probably easily have from Mesa, you know, from clinical variables to biomarkers to imaging markers and many, many things you can pile up, which probably will help you for, you know, predicting. So how, where is sort of the balance in terms of sort of total return, which you can match with, say, 200,000 subjects, but you only have 10 variables, versus 5,000 subjects, you have 200 variables. The total sum is the same, let's say, but how does that work out in terms of these two different approaches?
Well, I think that if I understand your question right, then actually, to answer your question, then I think that the number of variables that are involved in the equation, we basically limited our study just to these specific variables. But if we were to like include multiple other variables, then we start off with something called feature selection. So we basically wouldn't just we allow the whatever model we were using, in our case as SVM, but we would allow the model to help determine which ones are important to it and which ones are not. And there are different methods of determining which features, so that some of the variables don't become so huge and unwieldy. You're basically, the model is going to select which features are important to it as far as being able to discriminate one class from another.
Yeah, so the AUCs were incredibly impressive for, just using those 9 variables. I guess kind of 2 questions come up. One is, a lot of us from prior MESA data where the reclassification index using corneal calcium beyond kind of typical framing and risk scoring was very strong. So that seems to be the natural thing to look at, whether corneal calcium score would push that AUC curve. It looks like there may not be a lot of room to push it further. So I was curious if you've looked at adding corneal calcium as kind of the obvious first thing to add. And then how does this compare? Because there was a MESA publication looking at machine learning using all of the MESA variables for risk prediction. And how do your findings compare to that publication?
Yes, thank you. So we have started looking at the effect of coordinator calcium if you add it to the model. Some of our preliminary work shows that there is an incremental improvement in the performance of machine learning when you do add coordinary calcium to the model. And so as far as the second half of your question was about.
Well, there's a publication from MESA where they looked at all the MESA data for prediction, and so how does this model compare to that?
Sorry, I don't know the particular article that you're talking about, so I can't address that. Matt, do you happen to know?
I don't know about the details. We'll compare the two.
I'm from Korea, and it's a great talk, and I'm not familiar with the kinds of machine learning, but I have one question is that the frame risk score and other risk score is not fit in your cohort. So if you make another classical model to predict the cardiac death, and then have you ever compared your own model by using your code and then machine learning algorithm?
No, we have not done that. No, we haven't.
All right, so thank you very much, Albert.